Welcome back, friends. In this lecture, we will be studying examples on Thevenin's theorem. So, let us straight away head to examples. So, example 1. So, in this example, the problem statement says that using Thevenin's theorem, find the current in resistance of 30 ohm. So, here there is a resistance of 30 ohm, that is RL, at which we need to find out the current flowing. Now to solve this, so the first step what we will do, we will remove the load resistance from the circuit and we will mark those terminals as A and B, and then we need to find out what is the voltage at those terminals. So here I have removed the load resistance A and B at A and B, and I have marked them as A and B, and now I need to find out what is the voltage across A and B. So when you closely look at the circuit, the voltage at points A and B is nothing but the voltage drop across resistance R2. So how can you find voltage drop across R2? It is just simply a voltage division rule what we have studied in the basics. That is VTH is equal to supply voltage V into resistance R2 divided by total resistance R1 plus R2. So that is 48 into 24 ohm divided by 6 plus 24 ohm. That turns out to be 38.4 volts. So that is the VTH. Now to calculate RTH, what I have to do? I have to replace the voltage source by its internal resistance. There is an internal resistance in the problem statement. So if you can just remember this slide, that is at V1 there is 48 ohm and 2 ohm they have mentioned, that is the internal resistance. So we need to consider that also during calculation of RTH. So RTH, so I have removed the voltage source with the internal resistance 2 ohm. Now we need to find out what is the resistance at terminals A and B. So when you look at the circuit from points A and B, so it's clearly sees that there is resistance R1 and internal resistance R are in series, and this series combination is parallel with the resistance R2. So RTS is equal to R2 is in parallel with R1 series with R. So that how can we write that? That is R2 parallel with R1 plus R. So that is R2 into R1 plus R divided by R2 plus R1 plus R. So that is 24 into 8. So here 8 refers to the series combination of R1 and R. That is 6 plus 2, that is 8. So 24 into 8 divided by 24 plus 8, that is equal to 6 ohm resistance. Now this RTH and VTH are in we need to draw the Thevenin's equivalent circuit. So they are keeping VTH and RTH in series and connecting back the load resistance that we have removed in the first step. So this is the circuit to calculate the load current. I am connecting back VTH and RTH in series. So and then connecting back the load resistance RL. So here this is the circuit to find the load current, the current that is flowing through the load resistance. It is very simple since these all things set up is in the series combination. So VTH is IL is equal to VTH divided by total resistance, that is RTH plus RL. So that is VTH is 38.4 divided by total resistance RTH plus RL. So RL is 30 ohm, RTH is 6 ohm. So 30 plus 6, that is 36 ohm. So that turns out to be IL is equal to 1.06 ampere. So this is how we will solve the network using Thevenin's theorem. So now let us study some more examples. So in the example 2, calculate the current in 4 ohm resistance. So can you identify where is the 4 ohm resistor? Yes, it is R3 resistance. R3 is a 4 ohm resistor. Now we need to find out what is the current flowing through this resistance. So according to Thevenin's theorem, so first we need to identify what is the load resistance, and then we have to remove it from the network. So here R3 is the load resistance, and I will remove that from the network, and I'll try to find out what is the voltage at those terminals. So here it is the first step, that is I have removed the load resistance R3 and I have marked the terminals A and B. Now I need to find out what is the voltage at terminals A and B. Now, since there are two sources here, and when I open circuit that branch, the voltage at VAB can be found out by applying KVL to the second loop, that is consisting of V2, terminals AB and resistance R2. So in this loop we can apply KVL. But to apply that, we should know what is the voltage drop across resistance R2. So to find out voltage drop across resistance R2, so since now R2 is connected only to V1, so you can easily find out what is the voltage across R2 using voltage division rule again. That is, so Thevenin at point AB is equal to, so that is actually it should have been voltage drop across resistance R2 is equals V1 into R2 divided by R1 plus R2. So that what is the voltage division rule says. So V1 into R2 divided by R1 plus R2. So that is V1 is 15 into 5 divided by 10 plus 5. So that turns out to be 5 volt. So 5 volt is the voltage drop across resistance R2. Now we can apply KVL to this loop. So KVL loop, that is, if you traverse from the that is the source voltage V2 and then through terminals AB and then to resistance R2, then it turns out to be like, so this is plus 6 volts and this is VAB and this is minus 5 volts. That is VAB, that is terminal voltage will be minus 6 plus 5, that is minus 1, or taken in the other direction, that is 6 minus 5, it is equal to 1 volt. Now to calculate RTH, so what we have to do, again we have to short the voltage sources and try to find out what is the resistance across the market terminals. So when you look back into this network at terminals AB, so these two resistance seems to be in parallel. So RTH is equal to R2 parallel with R1, that is 10 into 5 divided by 10 plus 5, that is equal to 3.33 ohm. Now the last step, that is we have to again draw the Thevenin's equivalent circuit using VTH and RTH and connecting back the load resistance. So here is the circuit, that is VTH is equal to 1 volt, and here see, since it was a minus 1 volt, so the direction is shown in the reverse order, and RTH is 3.3 ohms and load resistance is 4 ohm that we had removed in the first step. So now to calculate the load current, so IL is equal to VTH divided by RTH plus RL. So VTH is 1 volt divided by RTH plus RL. RTH is 3.3 ohms and RL is 4 ohms, so that turns out to be 7.33. So 1 by 7.33 is 0.13 ampere. So that is the load current flowing in the load resistance RL 4 ohm resistor. Now let's take one more example. Now here calculate the current in R3. So here it has a current source of 12 ampere and 3 resistance connected as shown. Now the first step is to remove the load resistance. So here the load resistance would be R3 and I will remove that from the circuit. So when I remove it from the circuit looks like this. Now to find out the Thevenin's voltage at AB, terminals AB, so that is nothing but the voltage drop across resistance R1. So voltage drop across resistance R1 or voltage across resistance R1. So that can be found out using I into R1. So I is 12 ampere and into the R1 resistance 4 ohm, that is 12 into 4 is 48 volts. So that is the Thevenin's voltage. So since no other source is acting here, so voltage drop across this parallel path is the voltage across that is a Thevenin's voltage. Now to find out RTH, since the source is a current source, the current source are replaced by open circuit, so it's been open. Now these two resistances R1 and R2, they appear as in series path at terminals A and B. So terminals is RTH is equal to R1 plus R2, so it is 2 plus 4, that is 6 ohm resistor. So now finally we should draw the Thevenin's equivalent circuit connecting VTH, RTH and RL, and try to find out what is the load current in the load resistance RL. So IL is equals VTH divided by RTH plus RL. So VTH, what is the VTH? It is 48 volts divided by what is the RTH? It is 6 ohm, RL is 7 ohm, so 48 divided by 6 plus 7, that is, so finally the answer is 3.69 amperes. This is how we will solve the various problems on Thevenin's theorem. So hope it is helpful. Thank you.